In this video, I want to have a great extent presentation on a research work that I, along with two other members from SBU University and a member from a private company which specialized in optical stage designs, have the key roles in designing, fabrication, and development of the device that we name it Plasens with.
The system has a straightforward and user-friendly appearance. In fact, it's a visible band angular spectrometer platform used in the optical analysis of nanomaterials, nanotechnology, and nanophotonics related industries. This system reduces laboratory complications associated with optical angular spectral measurements of thin films with nanometer thickness. This is the system's most significant and defining characteristic. The length, width, and height of this system are 738, 528, and 287 millimeters, respectively. The graphical touch interface on the system's front panel has significantly simplified the user's interaction with the system. The system's power switch, data transfer port, power supply port, and system ventilation fans are located on the rear panel. The Plasens platform has both automatic and manual movement for its cover. This cap's purpose is to improve spectral measurement quality, reduce optical noise, and prevent environmental dust from settling on the thin film. We will now explain the mechanical and software components of the Plasens system. When the covering is open, the following are visible to the user: circular, external, internal, and fixed moving plates, spectrometer holder and height adjustment, holder and height adjustment of the optical tube, prism holder, and thin film. All of these components are made of aluminum to maintain the rotation's repeatability and improve the system's precision. Regarding tube holders and spectrometers, it's important to note that each tube holder is equipped with an angular indicator. Due to the length of the tube, however, is not visible to the user using the light tube's indicator. The angular indicator on the spectrometer holder allows the user to view the angular position of the carrier. The purpose of these screws is to modify the height of the holders in relation to the surfaces of the rotating plates and the fixed plate. The user can modify the height of the light spot exiting the optical tube and the position of the light spot entering the spectrometer lens by turning these screws. Using the index of the spectrometer holder as a height measurement tool, the minimum height from the surface of the rotating plates is 5 mm, and the maximum height at which the holders can be set is 30 mm. This screw is also used to modify the spectrometer's distance from the holder. At the closest distance, this screw places the spectrometer lens at 2.5 cm, and at the farthest distance, the lens is placed at 4.5 cm from the thin film holder. The optical tube's optomechanical mechanism allows it to supply linearly polarized S and P light to the sample. It should be regarded as a source of light in both radiant and reflective modes. This broadband light source optically excites the sample film at multiple visible wavelengths. The mechanism utilized by the Plasens system to alter the polarization of light is the circular rotation of the Glan-Taylor prism. This is accomplished mechanically by a gearbox placed on an optical tube. In order to better comprehend the performance of the radiation and reflection modes, we will now discuss the system performance schematic. The film is positioned in its holder perpendicular to the radiation direction of the optical tube and the spectrometer, as shown in the schematic associated with the radiation mode. The film in radiation mode ought to be made of a substance with a high optical transmittance. This is necessary so
that the spectrometer can clearly display the spectrum of the transmitted light. In the Plasens system, the radiation mode is only taken into account for the 0-degree angle, when the optical tube and the spectrometer are in the same direction and facing one another, because the angle is not discussed in the radiation mode. In a way, Plasens platform's reflective mode is its most crucial component, the two revolving plates being to rotate simultaneously towards one another in the holders of the spectrometer and light source. The most crucial aspect of the reflection mode is the thin film's reflection angle. The spectrometer samples the spectrum of light reflected from the thin film surface at any angle where the light source is located. This mode is suited for films with high reflectivity as indicated in a schematic. STS-Viz is the type of spectrometer used due to its small dimensions, 40 by 42 by 2.4 mm, and its wavelength range, which is in the range of 350 to 800 nanometer. This is because the type of light used on this visible platform is polarized. This item is from Ocean Insight Company. Two types of film holders have been designed for the reflective system, as depicted in the image. In the first case, a semi-cylindrical prism can be used. The second mode is for non-dependent prism films or metasurface films. In radiation mode, the film holder enables the transmission of light. In general, the air gap in holders of this type can accommodate films with a maximum thickness of 1.5 mm and minimum thickness of 0.1 mm. The standard length and width of the films are 18 mm by 18 mm. However, users can increase these dimensions to 20 mm by 20 mm. The semi-cylindrical prism for the reflective holder has dimensions of 19 mm in height and 20 mm in diameter. After a brief introduction to the system, we can now proceed to the Plasens system software. Since reflection and radiation evaluation of thin films in optical laboratories is a time-consuming and error-prone process, Plasens software attempts to make measurement in the minimum time and with a few errors possible. After launching the software, the user is presented with a page containing the name of the following keywords: GRTC, which stands for Characterization of General Reflection and Transmission; IMPS 1, which stands for Internal Memory Projects 1; IRAC, which stands for Ellipsometry Reflection Angle Characterization; IMPS 2, which stands for Internal Memory Projects 2, and the OFF key. The GRTC menu is where we begin. To properly perform spectral sampling, the user must first set the angular parameters for the system in this menu. The user can access the following keys by pressing the GRTC key: setup angle, spectrometer, transmission, reflection, observe the results, save results, transfer data, and back to main. Only keys that are currently in use in this window are setup angle and back to main, which are represented by the colors red and green respectively. Pressing the setup angle key brings up a menu with several rotary and push buttons. Here we will start by discussing how each of these keys works. Then we will demonstrate how they perform during practice. We begin with the step rotary key. This key represents the starting angle point. By rotating this key, only 0 and 10 degrees are displayed on the display associated with this key. If the 0 option is selected, the radiation of the GRTC system will be activated. If set to 10, both the reflective mode and the starting angle are activated and set to 10 degrees. The second rotary key is labeled DAP, which stands for distance angle point. This key determines the sampling distance in terms of angle. This key has an angle range of 0.1 to 0.5 degrees. This key is only active in reflective mode and inactive in radiation mode. SWL, which is the third rotary key, stands for stripping window length. This button enables the user to set the arm's rotation window between 40 and 60 degrees. Likewise, this key is inactive in radiation mode. IT is the final turning key, which stands for integration time. This key relates to the sampling time for the platform spectrometer. This value can be altered between 100 and 1000 milliseconds via this platform's software. By default, this value is set to 800 milliseconds in all radiation and reflection modes. In the LPCP panel, which stands for lamp control panel, the user can guarantee proper lamp operation by turning on and off the lamp, which emits incoherent light for the light source. Lamp on is used to switch on the lamp, while lamp off is used to turn it off. When the on button is pressed, the button becomes inactive, and the lamp off button becomes active. The DRCP panel allows the user to open and close the device movable door. It should be noted that this door, which slides open and shut, can be opened and closed both manually and through the software. The door is equipped with microswitches that inform the user of the door's position. DCK represents door check. If the door microswitches are functioning normally, one of the two keys, DOS, door open switch, or DCS, door close switch, will be activated. In this panel, the DSS key also stands for door stop switch. This key can only halt the door when it is in the motion and the microswitches are malfunctioning. The next panel is called LASACP. This panel positions the optical and spectrometer arms at the device's 0 degree position. The user sees the title SAS on the left side of this panel, which stands for spectrometer arm status. Below that are indicators for ZP 0 point, SSZP, security switch 0 point, and SSEP, security switch endpoint. The identical indicators are also displayed on the panel's right side under LAS, light arm status. It is evident from the title that the indicators on the right correspond to the arm of the spectrometer, while the indicators on the left correspond to the arm of the light source. With this introduction complete, we can now discuss the operational duration of these indicators. If the user selects the MS-ON key, abbreviated as motors on, it activates or energizes the motor associated with the arms. Next to the MS-ON key is another key labeled CH, which stands for check. This key and the fourth key of this panel, MS-OFF, which stands for motors off, are activated and turn yellow when the motors are turned on. If the user does not wish to examine the positions of the motors, he can deactivate the function by pressing MS-OFF. The arm motors are deactivated and the MS-ON key is activated. To check the position of the arms and set them to a 0 degree angle, however, he must press the CH key. When this key is pressed, two ZP indicators can display either green or red. If the indicator is green, the arms are at 0 degrees. If it displays red, the arms are not at an angle of 0 degrees. Notably, the ZP indicators are linked to optical sensors that are precisely positioned at 0 degrees. Other indicators, SSZP and SSEP, are linked to electronic microswitches that can indicate the position of arms at -2 degrees and 90 degrees, respectively. When the CH key is pressed, these indicators should illuminate in red. If the ZP indicators turn green, the SH key remains off because the arms are positioned at 0 degrees. If they display a red color, however, the SH key will be activated. The user must press this key for the system to automatically position the arms at 0. If the optical sensors associated with the ZP indicators are malfunctioning for any reason, the arms may turn to position less than 0 degrees. As a safety precaution, SSZP microswitches correct the motor's rotational position in this case. In this instance, The indicators associated with these macro switches turn green and the motors return to 0 degrees. If for some reason the sensors did not function properly on their way back to the engines, the SSEP macro switches will be activated and their indicator lights will turn green. In this case, the movement of the arms is halted by the macro switches, and the user is prompted to check the hardware of the optical sensors via an error message. Now, to obtain additional information, we press the check key and observe that the OS key is active. Then we press this key to access the system again. A message appears on the screen instructing the user to wait until the door has fully opened. The user can see the spectrometer arm, the light source arm, which carries the polarization changing gearbox, the prism, on which 35nm thick gold film is placed, and the calibrated and fixed plate after opening the door. The prism holder and adjustment screws are visible. Here, for the device's practical test, the initial angle for a reflective mode is set to 10 degrees. We set the angle step at which the arms do the sampling to 0.5 degrees. We set the length of the angular sweeping window, which is adjustable between 40, 50 and 60 degrees to 40 degrees. We set the photon sampling time parameter, also known as integration time, which ranges between 100 and 1000 milliseconds to 800. This is due to the fact that sampling accuracy is acceptable and accurate. Pressing the setup key will display a message once the aforementioned items are set up. This message reminds the user of the entire set's summary. In this instance, the beginning angle is 10 degrees, the sweep window length is 40 degrees, the angle step is 0.5 degrees, and the final angle is 50 degrees. Then we test the lamp to determine whether it turns on or off correctly. We turn off the lamp and adjust the arm's 0 position. By pressing the MS-on key, both the CH key and the arm motor are activated. In the subsequent step, by pressing the CH key, the arm indicators will turn on. By observing the green mark on the location displays of the light source arm and a spectrometer, the user can confirm that both the spectrometer arm and the light source are in 0 degree position, or ZP. Red marks also indicate that other sensors are operating properly. In practice, they should always be red to demonstrate that the arm position is adjusted to 0 degrees. The greening of any of the SSZP or SSEP indicators may indicate a hardware issue with the ZP positioning light sensors. To improve the quality of the measurement, the user can close the device's door before performing the measurement. Here, pressing the DCS key closes the system door. It should be noted that the measurements are also possible with the door open. We will now close the system's door by pressing the back key. All changes will be saved and the page will be reloaded. In order to better comprehend the operation of the arms, left the system's door open and repeated all previous operations. We can see that the spectrometer key is red and all other keys are disabled, with the exception of the back to main key. This indicates that the permission to access each key depends on the key that precedes it. If each key press is successful, the user will be granted access to the subsequent step. By pressing the spectrometer key, the corresponding window is displayed. We are immediately presented with a page containing numerical displays, operating displays, sensor displays, 4 buttons labeled back, stop, capture and initiate, and an empty graph. The horizontal axis of this empty graph represents the received light's wavelength in nanometers, and its vertical axis indicates the light intensity received by the spectrometer. To begin working on this page, the initiation key must first be selected. This key is used to turn on the lamp and spectrometer, test the spectrometer, check the position of the arms, and set the polarization of the light source arm to S mode. After pressing this button, all operational displays and sensors become active. After these explanations, the initiation key is pressed. As a test of the spectrometer's performance for the user, it displays a spectrum at 0 degree angle.
The zero-valued numerical displays of the angle indicate that the test was conducted at this angle. The lamp, spectrometer, polarization, door opening, and zero position of the arm turn green on the indicator screen. By pressing the capture key, angle spectroscopy is initiated. Initially, the motors begin slowly rotating towards the desired angle. In this case, the user is also presented with a message regarding the return of the engines. All spectral diagrams associated with S-polarization are colored red. Due to the importance of S-polarization for spectral sampling, phases appears in all graphs. The arms begin rotating around the thin film with a half-degree angular step. Based on the phenomenon of total internal reflection, the output light is reflected towards the spectrometer after striking the thin gold film. The distance between the spectrometer's lens and the type of lens is designed to minimize light refraction to the greatest extent possible. Finally, each angle's spectral data is analyzed in real time. The stop option in the spectrometer's window is intended for the user to stop sampling in order to stop the rotation of the motors and, if necessary, stop the measurement. Arm movement and spectral sampling continue until reaching the final angle. When the arms reach the user-defined angle of 50 degrees, the user is notified that the arms have returned to the zero position. Then both the light source arm and the spectrometer arm return to the zero position. After completing this step, the optical arm's polarization changes to P. The previously red display associated with P polarization now appears in green. The arms begin sweeping again at a 10-degree angle. Here, the graph's color is changed to blue and its name is changed to phase P. It also displays and stores the arm angle graph for each sweeper in the device memory. As an illustration of the precision and performance of the device, we have chosen a 35 nm thick gold film to demonstrate the plasmonic phenomenon, which begins to form at an angle of 41 degrees. As the angle steadily changes, the phenomenon of plasmonic formation is evident here. With each increment of 0.5 degrees of shape depression, the spectrum and so-called absorption increase. Concurrently, the transition of this dip's wavelength towards longer wavelengths is evident. Almost no absorption occurs at an angle of 46 degrees. The spectral graph also clearly displays this phenomenon. In P polarization, the arms continue to sample until they attain an angle of 50 degrees. Similar to S polarization, after attaining this angle, they return to the 0-degree position. After reaching this point, a message regarding successful sampling will be sent to the user. Upon releasing the OK and back keys, the user is returned to the GRT main menu. It is important to observe that the system requires time to store the recorded data. Consequently, a message instructing the user to wait will appear on the screen. A red box will appear on the reflection button. Because the user has set the system type to reflective mode, after the successful completion of the spectral sampling, the user will only have access to the reflection option. In fact, the primary function of this key is to perform a data analysis operation on the taken spectral samples. By selecting this key, the corresponding window is opened. Upon entering this window, a blank graph, wavelength selection keys, Gulli setting keys, and row and back buttons are displayed. The vertical axis in this case is intensity. In degrees, the horizontal axis represents the angle. We begin by selecting the read data option. We are awaiting the system's collection of all data for analysis. After deactivating the read data button, the user can select the desired wavelength for the intensity graph to be displayed in the terms of angle. For instance, we select the wavelength of 337 nanometer. As can be seen, the draw key is now active for the user after data acquisition has been completed. By selecting this button, Spectral graph of light intensity versus angle for S and P polarization type is displayed. Using the increment keys, we now select the wavelength of 429 nanometers. By pressing the drag key again, the graph associated with this wavelength is redrawn. When the user requires a graph with less distortion fusion, he can generate a linear graph by employing a filter that employs Golang mathematical function and establishing the filter parameters, which include the window length and filter coefficient. More detail is discernible with less distortion. By setting these parameters and selecting the drag key, you can view this graph. Plasmonic excitation at greater wavelengths, such as 569 nanometer, exhibits a more distinct behavior in P polarization than in S polarization. Drawing these distinctions, a spectral diagram at a 45-degree angle facilitates its recognition. Even at longer wavelengths like 617 nanometer, changes in angle and spectral shift can be observed. The user can also examine the decrease in absorption at higher angles, such as 47 degrees at 730 nanometer. Each time the draw button is pressed, the data associated with the drawn spectrum will be saved in the system's memory for user review. By selecting the back key, the GRTC window is returned. You can see that the user has access to the Observe Results key. The user can view all image results from spectrometry and data analysis operations in this window. Here, the SIW key displays the spectral graphs for the S polarization. Observe the graph from greater angles. The user must press the right arrow key. The PIW key is used to display saved images of P polarization related spectra. For instance, the user intends to examine plasmonic spectra captured at the angle less than 47 degrees. Here, it is sufficient for him to select the left arrow key to see the spectra from lower angle. By pressing the IAF key during the discussion of data analysis, reflective data, the user can observe the spectrum of light intensity in terms of angle for a specific wavelength that was transmitted through the filter. By pressing the IAUF key, it is also possible to examine the spectrum not passed by a filter. By selecting the back button, we return to the GRTC's main menu. The Save Results button to choose a name for the completed assignment is seen to be active. Upon entering the window, the user sees a keyboard above which he is prompted to give the project a name. For instance, we select the name Plasens 1. Next, we select the Save option. Confirmation message indicating that the creation of the project name was successful is displayed. Pressing the back button, the GRTC primary menu is accessed again. The transfer data key is highlighted in red when returning from the Save Results menu. This indicates that the system is prepared to load all of its temporary memory into the newly created project. By selecting the Transfer Data key, a window describing the steps for transferring data to temporary and external memory is displayed. We see Check, Eject, TIM, TM, and Back keys. The Check button is used to check the presence of external memory in the system's USB interface. If there is no external memory in the port, selecting this key will cause the system to display an error message regarding the absence of external memory. If for any reason the user does not wish to keep his information in the external memory, he may do so in the internal memory of the TIM system. The information recorded in the TIM memory cannot be transferred to the TM memory. Here, the successful transfer message and a list of previously saved projects can be viewed by selecting the TIM key. Suppose we wish to store data on an external memory device. In this instance, we first inserted the memory into the system's backside USB interface. After loading the external memory and selecting the check key, the user will see a message containing the name of the external memory. The user can confirm that the TM and eject keys have been activated to transfer data to the external memory by pressing the OK key associated with this text message. By pressing this key, the user will see a list of folders in the external memory. A text message related to waiting for the user to transmit data will be displayed upon pressing the TM key. Depending on the volume of data, the procedure could take several minutes. In the majority of image files, all image information displayed by graphs is transmitted to the user's external memory. Additionally, numerical data contained in the majority of Excel files is transmitted to the user's external memory. After the file transfer is complete, the user will be notified that the data transfer to the external memory was successful. By pressing the OK key on this text message, a new list of folders in the external memory will be displayed, which includes the user's project. By pressing the back key, the user accesses the GRTC main window. Back to main is the only active button in this window. All other buttons are inactive. Here, the spectroscopic operation for the GRTC window is complete, and the user can return to the system software's main page. The internal memory projects 1, IMPS1 button is used to compare projects stored in the user's internal memory. By pressing the IMPS1 key, the window associated with this key appears. 4 keys with the following names are visible. Project selection list from internal memory, plotting transmission vs wavelength graphs, plotting reflection vs wavelength graphs, and back. We select the first button to view the list of projects that have been saved. Upon entering, you will notice 2 columns and 4 icons. The only button that is active during logging is the IM list button. By pressing this key, a list of temporary memory projects will be displayed in the left column. In addition, the del list and approval or APPV list keys are activated simultaneously. Using the left arrow key, we select the desired project and transfer it to the right column. Consider that we intend to compare 2 projects. We transfer 2 projects to the list of selected projects in the right column. Only 4 projects can be relocated to the selection list or right column, which is notable. After selecting the project names, the APPV list key can be pressed. A message indicating the accomplishment of the selected list will be displayed together with the results. By selecting the del list key, the user can delete all of the projects whose name appears in the right column from the system's internal memory. By selecting the back button, we return to the IMPS1 key's main window. Reflection vs wavelength graphs is the only obvious key. We select it and enter its associated window. This window displays the screen with instructions for using the buttons as well as 6 buttons labeled PIWS, SIWS, 10x, 5x, 1x, and back. We select the SIWS key. In relation to the explanation of the keys, the key PIWS display a graph of the reflectance spectra in relation to p-polarization. In the meantime, the key SIWS displayed the polarization results for 2 selected projects simultaneously. According to the time required to load the graphs, the 10x, 5x, and 1x keys can reach the desired angle among the spectrum graphs in a shorter period of time. After simultaneously drawing 2 graphs, the angle related to them, which in this case is 10 degrees, is depicted at the top of the graph. The PIWS key becomes active, the SIWS key becomes inactive, and the arrow and X keys become active. By pressing the right arrow key, we can see the spectral graphs in relation to the larger angle, which is 11 degrees. Suppose we press the 10x button. If the user presses the right direction key, the 16-degree system of spectral graphs will be displayed. Additionally, the user can view the project names on the specified graph. Suppose we want to show the user the spectrum graphs associated with p-polarization. In this instance, we select the active PIWS key. As the user waits for the images to appear, messages will be displayed on the screen. After some time, it becomes apparent that the spectral images associated with p-polarization have been displayed on the screen in connection with two separate projects. To view the p-polarization spectral graphs associated with the dimension angle of 11 degrees, we select the right direction key. The user can then observe the spectral graphs of the two projects for comparative purposes. Additionally, he can see those associated with this polarization type. Here, you can return to the software's main page by clicking the back button and pressing it again in the IMPS-1 window. ERAC is an abbreviation for ellipsometry reflection angle characterization. As the term implies, ellipsometric parameters are displayed to the user in relation to the reflected beam at a particular angle. In general, the parameters of ellipsometry are indicated by the characters psi and delta, which are illustrated by the following equations. Rp and Rs in the preceding equations represent respectively the intensity values of the reflected light received at various wavelengths or frequencies of polarized light S and P in the visible band. In the context of elliptic spectroscopy, there are two fundamental parameters. Users employ them when discussing the customization of materials. The first is the parameter psi, which represents the ratio of variations in the intensity of the reflected polarized light in degrees. The second case involves the phase changes of these two reflected lights at different wavelengths, which are also measured in degrees in this case. Changes in these two parameters are dependent on the refractive index of material used for thin film's surface. Consequently, the measurement of these two parameters can be used to classify characteristics such as substances, concentration, type, size, and light absorption rate. Following this concise description, we proceed to the rack window. This window resembles the GRTC window in many ways. In terms of performance, there are few distinctions between them. The setup angle window is accessed. It is important to note that this system only operates in reflective mode. One of the names of rotary switches is stab, which represents the sampling start angle point and can be adjusted between 10 and 68 degrees. Another title, ref, which stands for reference angle, is a specific angle that user specifies for sampling only at that angle. This value can range from 10 to 68 degrees. SWL corresponds to the previous definition of sweep window length, which ranges from 1 to 4 degrees. Integration time variety is the duration of each spectrometer sample, which is between 100 and 1000 milliseconds in this case. Here, the user can validate the proper operation of his system's light source by pressing the lamp on and lamp off keys. The device's cover can be opened and closed as described in relation to GRTC. The user can simply upload a sample of thin film. Here, we leave room for ellipsometry of the existing gold thin film. By selecting the MS-on key, we activate the light source and spectrometer arm motors. By pressing the CH key, the position of the arm is examined. Both arms are visible in the 0-degree position. Now that the sample has been inserted and reminder of the system evaluation has been completed,
without problem, we can define the ellipsometry test parameters for the system. Start angle is set to 10 degrees, the reference angle is set to 16 degrees, and the sweep window length is set to 1 degree. Select the setup option. The text message confirming the user's setting is displayed on the screen. Starting angle was 20 degrees and the ending angle was 21 degrees. After pressing the OK key, SPAP display will also display the text message for the end angle, where the arms stop. After pressing the back key, the rack window will appear. We observe that the spectrometer is on. Consequently, the system setting in the setup angle window are accurate. Select the initiation key after entering the spectrometer window to test the spectrometer, lamp, polarization, and arm position. The black spectrum and the green keys pertaining to S polarization, the lamp, and the position of the arms indicate that elliptic spectroscopy can be initiated. Considering that the initial reference angle for S polarization was 16 degrees, the arm moved towards this angle and create and save a spectrum graph at this angle. The polarization is then automatically changed from S to P and the graph is colored blue. After completing spectrometry at a 60-degree angle, the arms return to the zero position and an on-screen message indicates the return of the arms. Next, the arms are positioned at a 20-degree angle for an angular sweep. According to the settings in the S polarization, it first sweeps from 20 to 21 degrees with an angular step of 0.556 degrees. All of these procedures are performed in order. The user has no active role in the procedure. Additionally, the user can look over the indicators for any errors. When S polarization sampling is complete, the arms return to the zero position and on-screen text notice is displayed. After returning to 0 degrees, the polarization changes from S to P and the arms move towards the target angle. The graph associated with the P polarization reflection spectrum is blue. In the companion status panel, the P polarization indicator turns green. Again, the sweeping angle is between 20 and 21 degrees. After the arms reach the target angle of 21 degrees, spectroscopy ceases, and the arms return to their initial position of 0 degrees. A text message will be displayed at the conclusion of the scan to notify the user that the measurement was successful, because no error occurred during the spectral sampling. After selecting the OK key of this text message and then the back key, the user is returned to the rack window after a few seconds of waiting for the data to be saved. As implied by the name normalization, this system enables the user to normalize his data. First, we will click the Read Data button. It should be noted that after loading the spectral data, the user must select a normalization angle between 20 and 21 degrees from the angles he has already chosen. Loading data takes some time. After successful loading, the user will have access to the Draw key and the Angle selection keys, which are 4 yellow keys in the upper right corner of the screen. After selecting the Draw button, the graphs of the reflection spectra S and P are simultaneously drawn for the user's selected angle of 20 degrees and the reference angle of 16 degrees. Please check to include Ref data is a checkbox in the GUI filtering panel that allows the user to subtract the target angle data from the reference angle data prior to normalization. This action is to observe the changes in light intensity at different wavelengths. Note that after each modification or selection, the user must press the Draw key in order to view the changes. Here, after subtracting the spectrum of the target angle from the reference, the NSG or normalized S-graph key is pressed. The graph is depicted in black with the title NS spectrum. This is the normalized S-spectrum graph. Immediately following its creation, the NPG or normalized P-graph key is activated. This graph is also presented in black with the label NP spectrum. Suppose the user intends to choose a different target angle. For instance, a 20.70 degree angle is given here. To display target and reference spectral graphs for S and P, draw key should be pressed. Then, to reduce the graph's distortion and noise, we can select the option to filter the signal, similar to the Gaulish filter described in GRTC. For instance, this filter's window length is 103 and its coefficient is 1. After selecting the draw key, the data filter is applied, and the spectral graphs display a more linear and less distorted state. We press the NSG key. The normalized graph of the S spectrum is now drawn with the higher quality than before. The NPG key is activated after the spectrum graph is drawn. By selecting this key, the P-polarized spectrum is drawn after being normalized and passed through a filter with less noise. When the back button is pressed, the user is returned to the rack menu. The ellipsometry option has been activated in order to extract the ellipsometry parameters. After entering the empty graph ellipsometry window, the sample window length selection panel, psi and delta graph drawing buttons are visible. In the panel pertaining to the length of the sample window, the user can enter a value between 10 and 500 as the number of samples that the software should select from 1 to 1024 wavelengths. Calculating the graph of ellipsometric parameters will take longer and be more precise if more samples are utilized. As an example, we select the option 50 for sample analysis. The software selects 50 wavelength sample and their associated light intensity values within the wavelength range of 350 to 810 nanometer. Two spectra, S and P, participate in the calculation of the phase shift graph. The process of phase changes, which is used to calculate the integral associated with the ellipsometric delta parameter, is depicted graphically for the user. After the integral calculation is complete, the psi graph key is enabled for the user. By selecting the psi graph key, the user is presented with the graph which was generated using 50 samples. By selecting the delta graph key, the user is presented with the delta graph which was generated using 50 samples. After completing the ellipsometry window, pressing the back button will return you to the rack window. After accessing the rack window, the next bright key is the observe result key. By selecting this key, the associated window will open. We can see the four keys PSTGT ref, NP, NS, EP and ED, as well as the page of the instruction for using this window. PSTGT ref spectral graphs illustrate the relationship between the target and reference angles and S and P polarization. NP represents the normalized P polarization spectral graph, while NS represents the normalized S polarization graph. The EP graph depicts the spectral ellipsometry result for psi, while the ED graph depicts the spectral result for delta parameter. This window is intended solely for reviewing the rack analysis section's result. By selecting the back button, the user can view the Enable Save Result button. As is evident from the image, from this point forwards, project naming and saving in the rack system are identical to the GRTC window. Assuming the user has gathered sufficient information about this section, we proceed to the IMPS2 key in the main window. By selecting IMPS2 key, the associated window is opened. We encounter the following four keys: project selection list from internal memory, plotting S and P spectrum graphs, plotting NS and NP spectrum graphs, plotting psi and delta spectrum graphs, and back key. This key and its associated window are used to access and compare the results from at least one and no more than 4 spectrometers. The user can access the corresponding window by selecting the project selection list from the internal memory key. Similar to the explanations given in connection with IMPS 1,
The user can select and move the desired projects from the right column containing the list of selected projects by pressing the I am list key and pressing the right arrow key to the left column containing the list of selected projects. The user can then access the page associated with the IMPS2 window by selecting the OK key, the APPV list key, and then back button. When the user presses the plotting S and P spectrum graphs key, the associated window is displayed. In addition, the user can observe the S polarization spectra of the two selected projects in a single graph by pressing the S spectrums key. The observation is also made for P spectrum's P polarization spectra. To view the normalized graph, the user must press the back button and then select the plotting NS and NP spectrum graphs button. Similarly, by selecting the NS spectrums and NP spectrums keys, we can simultaneously compare the spectra of two distinct projects. To view the ellipsometry results, select the plotting and spectrum graphs key to display the spectrum graphs associated with psi and delta for the temporary memory stored projects. The explanations provided up until this point pertained to the menus used in association with the reflective mode of the Plasens system. In this section, we will explain how to use the radiation mode menus and hardware component. It should be noted that this system's radiation mode only applies to the GRTC and IMPS1 windows. Before we begin working with the radiation spectroscopy menus, we will first explain how the user should install the thin film sample. The thin film can be inserted into a thin slot on the small holding stage, which can be readily inserted or removed from the system. A spring pin, denoted by an arrow, presses on the portion of the film that is inserted in the gap in order to fix it. The pressure applied is sufficient to fix the film in place without causing it to shatter. The slot and holding mechanism is designed to accommodate films with thickness between 0.1 and 1.5 mm. To insert, we need to first pull the pin outward to create a space in the slot for insertion. After placement, enable the plate connected to the pins and to hold the film in place using the pressure of its own spring. This form of holder is intended for use in radiation mode. Therefore, light is emitted from one side on the film and enters the spectrometer from the other. We put the holder containing the inserted thin film on the fixed and calibrated plate of the Plasens system. Note that in order to remove or insert the thin film holder, the light source arm must be removed from the zero position. The user should position it at an angle so that he can easily remove the film holder from its fixed position and remove it from the system. After loading film into the Plasens system, the arms have to return to their zero position. By selecting the CH key in the LSA CP panel, the user will see that the spectrometer arm's green indicator is in the zero position in the setup angle window. However, the red indicator arm of the light source is not in the zero position. By selecting the SH key, the user sets the arm of the light source to the zero position. The displayed message instructs the user to wait until the arms reach the zero position. Aside from the step panel, the remaining rotary switches are off. As it is in the radiation spectrometry mode, once these conditions are met, this panel's display indicates 0 degrees. Here, the user needs only press the setup key to activate the system's radiation mode. After pressing this key, a confirmation message will appear to validate this process. To proceed with the spectroscopy, the user can select the OK button and then the back button. Upon returning to the GRTC window, the user will notice that the spectrometer button is now enabled. By selecting this key, the associated window is opened. Again, by selecting the initiation key, the user can begin with the spectroscopy test. After lightening the lamp indicators, adjusting the angle of the arms, and observing the spectrum on the screen graph, the user can press the capture button. By pressing the capture button, the system can execute radiation mode spectroscopy. Therefore, we proceed to open the spectroscopy capture key. The first spectrum illustrated in red.
corresponds to S polarized light. Instantaneously, the polarization of the arm of the light source changes to P. The next spectrum depicted in blue is the P polarization spectrum. At the conclusion, the system software will display a message to the user regarding the success of the spectroscopy. The user can return to the GRTC window by clicking the OK button in this text message, followed by the back button. When the transmission button is pressed, the system's radiation mode is activated. To access this window, the user must press this key. If you click the read data button in this window, the radiation mode spectroscopy data will load first. Activating the Golgi filter will reduce distortion and wave noise in the user's spectral signal. Here, we turn on the filter and press the draw key. Two spectra associated with the S and P polarizations are displayed here, with their graphical quality substantially enhanced. By selecting the back key, the user returns to the GRTC window. Here the Save Results button is in active mode. The procedure for designating and saving the projects is similar to that described in reflection mode spectroscopy. To avoid repeating explanations, we will now examine the IMPS-1 menu in order to discuss how to view data information saved in radiation mode. After saving radiation mode related data in temporary memory, the user can compare the results of multiple projects using IMPS-1. After accessing the IMPS-1 window, the user can see that the project selection list from internal memory key is active. By selecting this key, the associated window will open. By pressing the IM list key, the list of temporary memory stored projects can be viewed. On the left side of this window, the letter R is displayed after the name of some projects, and the letter T is displayed in front of some other projects. These letters, which are the abbreviations for the words reflection and transmission, are inserted in a pair of parentheses in front of the project name so that the user is aware of the radiation modes associated with his projects. Using the direction key, we transfer the radiation mode project to the left column. After the user presses the APPV list key, a text message affirming that the two projects selected for review are of the same mode type will be displayed. We press the back button to return to the IMPS-1 window after pressing the OK key on this text message. Here, we can see that the key for plotting transmission vs wavelength graphs is active. This key is used to observe and evaluate radiation mode related projects. By pressing this key, the associated window will open. This window contains the following four keys: UFST, UFPT, FST, and FPT. Here, UF and F stand for unfiltered and filtered respectively, and represent signals that have or have not been modified by the Golgi filter. ST and PT refer to S and P polarization radiation graphs, respectively. When the user selects the UFST key, for instance, the graphs of two selected projects related to S polarization that did not pass the Golgi filter will be displayed. Turning off the UFPT key displays these graphs with P polarization. In relation to the FST and FPT two keys, it is evident that the quality of the filtered graphs has been tangibly enhanced for the two selected projects. Finally, the user can return to the system's primary window by pressing the back button and the back button on the IMPS-1 window. After completing a spectrometry with the Plasens system, the user can shut down the device by tapping the off key. After pressing this key, the user will see a message instructing them to wait 30 seconds for the system to completely shut down and then press the system shutdown key, which is located on the back panel of the system. This video, which introduces and teaches how to use the Plasens system, has reached its conclusion. We appreciate your time spent watching this video.